I want to thank you for giving me the prized after lunch slot when everybody's, actually, the truth is I was originally scheduled for like 10 o'clock and I said, that is 4 a.m. my time, and maybe it would be better if I was in the afternoon, but then after lunch the last 2 days I wasn't been sure. But so we'll try to keep you awake and keep going. So today I'm going to talk about interactive task learning, but before I want to do that, I want to reiterate one key assumption in SOAR, and it's also shared by some other cognitive architectures, but not all. And that is that all deliberate reasoning in tasks is implemented in a uniform mechanism. There's one way for doing internal reasoning and for planning and for doing things in the outside world. So we don't have different representations. Like we don't ever, if you're somebody creating a SOAR agent, you'd never go and write in C or Lisp or anything like that. It's all SOAR all the time, and there's not different formalisms. It's all either the rules or things in semantic memory or whatever. And that's going to be important later for a hypothesis I have, but I just want to make that because I think it is a little bit different than the CRAM model, which is to have different components that have different ways of writing your program. So there is no architectural representations of plans. If we're going to do language processing, it is actually written using rules and this kind of operator type thing. So it is not that there's a separate way for doing other kinds of these subtasks. The other thing I want to reiterate, because it's important for one of the points of this talk, is that we see that there's, in these kind of cognitive architectures, there's two levels of learning. One of those levels is the architectural learning mechanisms. These are the mechanisms that are on all the time in the background, capturing knowledge as the system interacts with the world. So in SOAR, one of them is reinforcement learning. Another one is episodic learning, where it's just automatically storing episodes away. There's a mechanism I didn't talk much about, which is called chunking, which does procedure composition. It compiles problem solving in a subgoal into a rule. And so we have these automatic mechanisms always going on in the background. But then there's the idea that that's not really sufficient to think about how we do learning, and that there's these knowledge-based strategies which are implemented by having rules that are selecting operators, and those operators are doing things in order to create experiences for these other learning mechanisms. And we'll see an example of that. So one of the key things about learning strategies is they can be learned themselves and improved. But the architectural learning mechanisms cannot. They're fixed. I mean, I guess you could have ways of them being tweaked automatically a little bit, but in general, they're the fixed mechanisms always happening in the background. So that sort of provides some background for what I'm going to talk about today. So the question I want to answer is, how do you fill up an agent with knowledge? We saw some of the possible reasons this morning, possible ways of doing that, such as using existing knowledge bases. Mostly I'm going to talk about task knowledge. And so one way to do that is to write programs, but that is slow and expensive. So you say, well, but technology's come a long way now, and we have reinforcement learning, but that is slow and expensive. And when you think about it, when you look at things like learning the Atari games, it might look like it's magic and it happened really quickly, but in terms of the amount of experience those systems had in order to learn those games, it was on the order of years. And also in terms of expense, you're paying a lot of electrons in order to do that. So it can be expensive, and if you have to actually do it with experience with the world, it gets really expensive because reinforcement learning has a tendency to want us to do some exploration, and if that exploration leads you off the edge of a cliff to say, well, I guess let's see what happens. Can I fly? That's the end of your robot. Of course, we can do this in simulation, and so that's another possibility. But I wanted to look at a third possibility. So I don't want to say we don't want to do that. I just want to say there are other things that might be more effective. So the question is, what's another way of doing that? Well, back in 1958, so let's rewind a long time, John McCarthy had the idea for what's called the advice taker. And he said, the main advantages we expect the advice taker to have is that its behavior will be improvable merely by making statements to it, telling it about its symbolic environment and what is wanted from it, so you can see his perspective a little bit, To make these statements will require little, if any, knowledge of the program or previous knowledge of the advice taker. He saw that as you sort of making logical statements to it. Also, I think this is a real challenge to be able to interact with any kind of system that you're teaching it and not actually have a good model of what it already knows. But anyway, this sort of gives you the idea that the way we want to teach our systems is not by programming them, but to interact with them. So the idea behind interactive task learning is that we interactively instruct agents in real time, sort of in an apprentice-style learning, where they're learning all aspects of a task from scratch. Or they can build on existing knowledge that it already has. And the emphasis is on interaction via natural language, gestures, a shared context. So it's this apprentice-style learning where you, for example, are with the robot and you're telling it what to do, you're watching what it's doing, and it might be asking you questions because of things it doesn't know, and then you provide those answers. So it is really working together to solve a problem. And it's not just to tell it to do a task right now. So a lot of work in HRI is to how do we instruct robots to do different tasks, but it's that task at that point. This is how to learn a task, so after I've done the instruction, it can do it on its own. So we also want it to accumulate knowledge across tasks and build up on its previous instruction. So you do have to know a little bit about it, what it's learned before to be effective, because you want to be able to access what it's learned before. So I would claim, so from a cognitive architecture perspective, we thought this was a great challenge problem because it seems to require all aspects of what goes into a cognitive architecture. And when we build our systems, it does. So, oops, that's not supposed to be there yet. Let's see if I can make it go away. No, I can't. That's really stupid. I apologize. Let's just get rid of that. So there was a book that I wrote with Kevin Gluck on interactive task learning. It was actually the result of a week-long forum. It's called the Ernst Strungman Forum, and it was in Germany, and we had a great time, and there was about 40 of us there, and the book was the result of that. But anyway, so let's see how we go from here. All right. So I'm going to talk about a system, an ITL system we call Rosie, not very imaginative name, that's implemented in SOAR. Most of the work that was done here was done by Shivali Mohan, James Kirk, and Aaron Mininger, and I sort of supervised. So over the period of its life, it's been embodied in 4 different robot platforms. You'll see a few of them. 4 robot simulators. Actually, we can see some examples here. There's knowledge to implement language understanding and a L2 learning strategy. So that's what we build into the system. So it learns both mobile robot office tasks. So here it's learning a fetch task. This is that robot. Here it's learning some games. And here it's also doing some games. But the most important to take away from that is it's not specific to a given embodiment. So we can put it in different robots and different simulations. And you'll see some of that today. So I'm going to have 3 phases to the talk. The first phase is going to be about learning games and puzzles. That's sort of the environment. But the emphasis here is going to be on learning concepts. Because one of the things you know when you interact with a robot is I have to use terminology, and the robot might not know that terminology, so how do I teach it that terminology? So we're going to teach it games. Then we're going to talk about expanding the kinds of things we can teach to tasks. So these are going to be goal-based tasks. That's what games are. Then we're going to expand to what we call procedure-based tasks, where instead of giving the system a goal, you also often just tell it what to do and maybe intermix it with goals. And then the last thing is I'm going to talk about recent work we're doing, how to make it easier for the human to give instruction by using other knowledge sources. So we did games, which are goal-oriented tasks. Usually they're defined by a goal and constraints. So often you will say, this is an illegal state. And then a set of operators. The nice thing about that is that they're externally specified. We did not invent these games. We found them on the web. And so in one sense, we did not just teach it games that are easy to teach. And it does require lots of diverse concepts, actions, and goals, and we'll see that. And it learns these combinations from primitives and also from combinations of already learned concepts. So we build up hierarchies of concepts that way. And some of these concepts actually share between tasks. Sometimes the same name for a task is used, name for a concept is used in different tasks, and they don't mean the same thing. So we have to deal with that conflict. So it turns out that I still have the same problem I had yesterday, or 2 days ago. So we found out the solution is to do it this way. So here we go. So this is going to be an example, this is from like 5 years ago, of teaching the system to do the Tower of Hanoi problem. So hopefully you know what that is. If not, you're going to learn very fast. Because this is real time, there's nothing going on behind the scenes besides what you're seeing here. Except at one point we will go maybe faster than real time when it's executing the plan, just because it's kind of boring.
The name of the game is Tower of Hanoi.
Okay,
what are the actions and goals of the game?
You can move a clear block onto a clear object that is larger than the block.
I don't know the concept clear.
If a block is not below an object, then it is clear.
Okay, I now understand the concept clear.
So we had to define a new concept for it.
The action.
The goal is that a large block is on a right location, and a medium block is on the large block, and a small block is on the medium block.
I have learned the goal.
So that's all we need to learn Tower of Hanoi. And then he's going to say, go.
Done.
Done. And it's now solving the problem internally from what it just learned. Oh, and it solved the problem. And now all we're doing is executing the plan that it developed from solving that. And if you watch it, you'll see that it goes through and does it fine. And shockingly, it never drops any blocks. And this is what led us to do all that other work that I talked about 2 days ago. Because you have to have a good vision system that is keeping track of objects.
It was easy.
So that's the basic concept of what we're doing, and then we're just going to unpack that, okay? Because now you understand, okay? I hope you understand. So it's a task learning process is a level 2 using a level 1. So this is going to be the phases that the system goes through. It perceives the environment, builds up an internal model of what it sees in the environment. It asks and receives instruction, and the first thing it asks is, what is the task? What is the goal? It then comprehends what the human has said. It has a natural language parser. And if any new words come along while it's doing it, it will ask for redefinition or other definitions of them. Everything in blue I'm showing is where an automatic learning mechanism is saving things away into memory. So the blue parts are the architectural learning mechanisms that are part of this overall process. We then construct a declarative representation of the task. We ground all the things that it says into the world, and we try to make sure that we have definitions of them. And then we add a task, we describe that task as a network into semantic memory. We then use that network of information and interpret it in order to do internal planning to try to solve the problem. And as part of that, as we're interpreting those declarative structures, we're actually learning procedural knowledge, meaning rules that is specific to tic-tac-toe. And that gives us, although you can't see it, everything runs really fast, it gives us a 80 times speed up. So if we just stuck with the declarative representations, it would run 80 times slower than what it does. If we can't find a solution, it does find a solution here. It's able to look ahead and find a solution. If we had if we had 6 blocks, that wouldn't be the case. We would probably have a timeout, and the system would keep track that it hasn't been able to find the problem. It would then ask the human, well, what's the first step I should take? And we'll see that later on in another example where the human provides that interaction. But if it can provide this solution, then it does. And after that's going to, as it's solving the problem, it's creating a history of the actions it took, and those are being automatically added to episodic memory. And then finally, after it's solved the problem, it does a retrospective analysis where it goes back to the original state it was in and says, well, now what steps did I do along the way in order to achieve the goal? And why did and so that then lets it have a causal analysis of what had to be true at each step for it to select an action that led it to the goal. And that leads it to be able to learn new rules that are the control knowledge that it uses in the future in order to solve the problem. And I went over that really fast, but that's sort of what's going on here is we're learning multiple kinds of knowledge. We're learning not only the goal, we're also learning the actions that we take and the constraints on those actions, preconditions, and we're also learning selection knowledge about when we select the legal knowledge. And so that's all happening as we do this. So these are the L1 learning mechanisms that are all getting used. We actually aren't using reinforcement learning right now. We should, but we just haven't in order to do this. So to give you an idea of what that means in terms of knowledge and the memories, this is the knowledge that we write by hand. So I wished I could say, oh, we start up SOAR and it just starts doing task learning. Well, no. That is, as I said, the sort of L2 learning strategy. And so we end up having to write a lot of code in order to make this work. So we had to write the language parser. We had to write the system that created the mappings between words and concepts that are more primitive. So there's all this sort of stuff we have to do. We do have the learning mechanisms, and then this is the kind of knowledge that it's learning. And the colors don't really show. I'm sorry, it's very pale here, but hopefully you can see that there are lots of different kinds of knowledge that the system is learning. Some of that is language knowledge. It's learning to do new words that it's never seen before, but it's also building the task structures. And then, as I said, it's actually learning this action knowledge. So there's a lot of things going on in terms of learning. It's not just learning one type of data structure. We've done this with over 60 games and puzzles. Here they are. The key thing is that there's some board games. It turns out there's this whole class of things called river crossing games. There's grid puzzles like Sokoban, Knight's Tour. There's the side-swapping puzzles, there's block puzzles, Towers of Hanoi. There's these marking and logic problems like Sudoku, which we do a small version of. We don't do 9 by 9, or is it? Yeah, we don't do 9 by 9, we do like 6 by 6. And then there's other sorts of games. And we might even say that we do chess, but I guess we didn't claim it here. But if we do chess, it's a very simple game of chess. And same thing with N queens. We don't do 9, 8, whatever. We do a simple version of that, just because we haven't gotten the concept of attention in the system well enough so that we are doing instructions on attention. So the types of knowledge that are learned, as I said, just to give you examples, are goals, such as tic-tac-toe. The goal is that there are 3 captured locations in a line. Whenever something's in bold, that's a concept that is not primitive, that it has to learn through further instruction. There's actions. So in the frogs and toad games, if a toad is to the left of a frog and the frog is to the left of a clear location, then you can move the toad onto the clear location. And in this case, it has to further define clear and exactly what moving a toad means. There's failure conditions. If 2 of the locations are matching and they have the same row, then you lose. So we cast Sudoku as a game where you can lose or fail. And then there's heuristics, like prefer attacking a weak location. And so we have to define what attacking is in terms of the actions in the game, and we have to define what weak means in terms of very specific conditions, such as the number of armies on that location are less than the number of armies you're attacking with. And finally, there's a lot of task-specific terms you have to define, such as things being on the line or things having the same value. The classes of words that we learn in terms of language are nouns, these function words that are kind of interesting. If the last name, this is a husband and wives game, that's a river crossing game. If the last name of a woman is the last name of a man, then the man is the husband of the woman. It's very sexist. I apologize. That is not true for my wife. Her name is different. You'd never know that she was my wife, right? Based on this. So it's just but that's the way it's in the game. Okay, so we can learn adjectives, like if a bank is below the boat, then it is the current bank, because you need these terms. You don't want to describe a game in terms of the primitive objects that are out there in the world. You want to be able to create abstractions, and that's what we're doing with these words. And we even can define prepositions. So this is like a really hard one. If a location is next to an object, but it is not diagonal with the object, then it is adjacent to the object. And so you can see there's a lot of clauses and relative clauses and prepositional clauses, and we have to be smart about doing the language on that. I think we also can use pronouns like it, so it knows how to resolve it and stuff like that. Anyway, I actually wrote the parser. That was fun. Fun. And then there's, from these primitives, this is what we start the system, which is small enough so you can't read that. And then these are the concepts that we learn from that. Okay, so you can see that we more than double or triple the number of concepts that we learn. So one of the things that's kind of cool is that it turns out in these games that you see the same concept over and over again. And that's not because we decided to pick these games. But if you look at tic-tac-toe, you'll see the name of the game is tic-tac-toe, the name of an action is place, piece, and so on. And then you look at Three Men's Morris, which you've ever done. You might have noticed it's somewhat similar to tic-tac-toe. Well, it's more than that. So if we look at that, the colors come through. Everything in green is replicated on both sides, okay? So when we're defining tic-tac-toe, we define what a move is, and that's exactly what's true in Three Men's Morris. So if we have taught tic-tac-toe, then when we get to Three Men's Morris, this is all we have to teach, okay? Because now we've defined the concepts like place, piece, which is defined below here already for us, all right? So you might wonder, can we take advantage of that? I sure hope so. But one of the problems we might get is that we have the same word, but it's ambiguous. So it turns out from tic-tac-toe, we can get, if a location is not below an object, then it is clear. Okay, there's nothing on top of us. But it turns out in the marking type of tic-tac-toe, there's a different concept. So if you're marking things on a page as opposed to putting pieces, if there's no mark on a location, not an object, but if there's no mark on a location, then it is clear. And then we get to a game, and it's the frog and toads game, and it says if a toad is to the right of a clear location, then you can move the toad onto that location. Well, guess what? What do we mean by clear here? It turns out that there's no marks around, so all those positions are clear. But there is one clear location here that doesn't have an object on it. Which one should we use? Well, so what the system does is it tries to instantiate both into the world, and then it looks to see, is there a simple way I can ask a question for the human that would disambiguate between the two? And so what it does is the agent creates both interpretation, and then it says how many actions are present, 1 or 2. And so why is it 1 or 2? Okay, if this is the clear location, then there's only one action available. Yes, because you have to jump. But if there are, all of these positions are clear, then there's more than one action that can be taken, and so you have 2. So that's what we're trying to do, and we don't have a great theory about this, but this is supposed to show you that not only do you want to be able to identify when there's ambiguity, but you might not want to go back and try to say, well, are you picking the definition from tic-tac-toe where it's a location is whether it's below an object, which it could do. It could go back to these original definitions and spew them out at you. But it might be easier to do this kind of question asking. So anyway, that's something we tried out. So now we're going to show you the big evaluation in one sense. So we took 40 of those 60 games, and then this is what you have to get your head around. We created 1,000 randomly generated permutations of teaching one game after another. So I got 40 games. One permutation is there in alphabetical order. Another permutation is there in reverse alphabetical order. We didn't use alphabetical order, but just that way. And another permutation is another way. And so we're teaching one game after another after another. And then we're looking at how many words did it take to teach the game after we had taught those previous games. And actually what games those were was random, But we did 1,000 times, so there's some of our graphs are a little smoother than they would be. So we're going to evaluate the effect of transfer on communication time, which we do is count the number of words. And here's what we get. So each one of these lines is one of the 40 games, okay? And so all of the games, it looks like mostly, they start off, I need a lot of words. But as we're going through here, more and more of the other games have been taught before I'm teaching this game. So I've had the chance to learn more and more of the concepts in this game. And so what we see is that there's, you'll never guess what game that is because most people have never heard of it. But it turns out there's a game that is the combination of Sudoku and, it's a game I play every day. It's like Sudoku, but you have constraints that things have to add up into different. Does anybody know what the game is called? Anyway, I'm sorry, I forgot. I will remember by the end of my talk. But anyway, Killer Sudoku here is the combination of two different games, or the constraints of two different games. So it takes the most number of words in order to specify it. But as it has more and more probability that Sudoku's been taught before it or that other game has been taught before it, it is more and more likely to be able to use those concepts. So by the end, it starts off at 240 or so, and at the end, it's about 60. So there's a 4-time improvement in terms of the number of words required. However, there's a couple games that have essentially very little transfer with other games. Oh, the talk has gotten so bad, he has to leave for the airport. Bye-bye, thanks for your talks. So Frogs and Toads, it turns out, does not have anything that's similar to other ones except for clear. So that's why we get very little benefit from teaching other games before it. And it turns out the blocks world is the same thing. So I think, so maybe it's clear and on top. And those are, well, no, I think on top is pretty primitive. Anyway, so you see that the average game is getting significant benefit, but there's a lot of games who we get to a certain point and essentially everything we can learn from other games is there. But we are getting transfer. So that's the end of my discussion of games. I'm going to now talk about, well, can we expand the kinds of tasks we're doing? Games are one kind of task, but it's actually not trivial always to come up with a goal to describe the task you're trying to achieve. So what we want to do is look at diverse task formulations. So we want to be able to include goal-based, just like we did before. And the cool thing about goal-based ones is once you know the goal, if the system has learned the operators, it can do its own internal planning to solve the problem. But sometimes there's tasks where it's really hard to come up with the goal, and what you really want to do is provide a procedure to the system and say, do this, do this, do this, and now if you've done all those things, you've done the task. And so it's really hard to give that goal description at the end. And then there's also, we want to be able to have hierarchical tasks where I give a description of the actions or whatever to provide at a top level that's pretty abstract. I don't have to go down to my primitive actions, and that I then can describe each one of those in terms of either a goal-based task or a procedure-based task. So that we have this sort of mixing of things. We also want to be able to learn diverse action types. Everything I talked about before was a movement in the world, placing a piece or whatever. And those are sort of physical actions. But it turns out that many times when we're doing a task, we have to communicate with somebody else. We have to tell them something, or they have to tell us to them. So we wanted to expand the set of actions to include communicative ones. And we also want to have mental ones, such as remembering something, and perceptual ones, which is looking around. And we wanted to expand the kind of modifiers so we can have controls and temporal constraints. So this is the environment in which we did this work. It's sort of a barracks, and we're teaching this robot right here to move around through the barracks and do certain tasks. So the types of task knowledge that the system's going to start with is some innate pre-programmed knowledge, such as the building layout and the primitive actions. It also is going to have knowledge that it's learned from earlier instruction that's too boring to show you for these demos, like how to fetch an object. But then it's going to have instructions that are taught for a task we call interior guard. Think of it as patrolling and that. So this is going to work on its own. So we're teaching it to inspect a room. And so this is telling it to go to that room. And then, as you'll see, now that it gets in the room, it has some primitive knowledge that it knows it has to scan the room before it gets any instruction, just because that's a good thing to do. And asks, what's the next step of instruction? And it says, if the light switch is off, then turn the light switch on. It's got good sensors, but it always helps to have the light switch on. So it turns on the light switch. It then tells it a next task, which is conditional. If you are in a sentry post and an extinguisher is not present, then fetch an extinguisher from the supply room. Well, it turns out there's a fire extinguisher in this room, so it doesn't do anything. And then the next instruction says, if the current location is empty, then turn off the light switch. Well, it's not empty, so it doesn't turn off the light switch. And then it says, you're done learning about that simple kind of instruction. So now we go to inspect the mess hall. And we've already learned about the other kind of inspection. So we go in here, there's nobody here, we turn on the light, and then we interrupt its instruction and say, here's other things you should do. If you are in a mess hall, so now we're going to have specialized instruction for being in the mess hall, and it's going to be that the plate has to go into the sink. And so it does some planning on its own to figure it out. That's a goal-based task. So here we're seeing some instruction of what to do next, but some also where it figures things out. If there's a condiment on the table, like ketchup, then you should put it in the refrigerator, and the refrigerator door should be closed. It's able to figure that out, and it only has one arm, so it has to open the refrigerator first and does that. So it does next, it says, what's the next step? And then it says, okay, continue inspect, and you'll remember that we said turn off the light. All right, so it turned off the light. So now it's expanded its definition of inspection for mess halls. All right, so let's look at the whole thing together, and this has gotten a lot more instruction because some of the instruction is if you should go from these rooms to these rooms in order to do it, and also if this guy shows up, you're done. And this is not going to work that way, so we do this, and off we go. This took 11 minutes of real time to teach. So the person says to it, guard the barracks, and it has learned to guard the barracks, and what you didn't see is that one of the things it learned about guarding the barracks is you should ask, who's my relieving officer? So that's something we taught it to do when it starts out. So now it knows, oh, I've got this officer, and it was taught to remember that. All right, so it saves it around. So now it's going to inspect the mess hall, finds a condiment, ketchup, puts it in the refrigerator. And we are going 6 times faster than real time because it's just too boring to watch it. Okay, so it comes here. Oh, there is no fire extinguisher. Remember, we never actually had that experience before because it already had it, but it did learn to do it. So now it's going to fetch the fire extinguisher. It's done with this room. It doesn't turn off the light. It's now going to go to the place where there's cars. It actually locked the car. And now it comes in here. Of course, somebody put a plate down. It's going to clean up the plate. So it's going around in a cycle through these rooms now. So that's the basic thing. It'll cycle through these rooms forever. But it comes in here, it notices Mercer's there, and it's done. Okay? So if he didn't show up, it would keep doing these things, keep doing these inspections, and dealing with people doing nasty things to it. Okay. So in terms of the different tasks and subtasks, this is what it learned. These are procedural tasks and subtasks, the ones in blue. All these ones down here are innate ones that it started with, and everything else in between are ones that it learned and how to put together. So it had to learn, pick up, how to ensure that things are going right in that one, how to do the inspect, and so on. So this is all learned by the system. All right, so let's take a breath. It still takes 11 minutes to do this. It still feels like sometimes I'm giving an instruction it should be able to figure out. So when did it seems like there's these knowledge sources out there that people claim just know everything about the world. Now, we have the knowledge sources that we talked about before, but but there's other knowledge sources out there. So what did we decide to do? We decided to look at ITL integrated with large language models. And that means SOAR integrated with GPT-3. So we integrated GPT-3 with SOAR as an external knowledge source for interactive task learning. We prompt GPT-3 and say, we want to do this task. What do you know about that task? And the crazy thing is GPT-3 knows something about almost everything, but you don't want to trust it about anything, okay? That's the other thing. And it knows some things, but you know, it might not be embodied. The knowledge is not about your embodiment. So our robot has only one hand. So maybe most instructions for cleaning things up assume that you have two hands. And so it will tell things that it can't really do. So there's some overlap with some recent work done at Google and DeepMind. And you'll notice how many people are part of our research. There's me and Bob and James. And there's 42 people on this paper and 23 people on that paper. So it's a weird world. Anyway, so how do we do this integration? We have an interaction with the GPT-3 interface. We go out on the web and ask it questions, and it tells us things. And it's really fast. I mean, it's faster than I would have expected. So we will maybe give it a task and say, we want to tidy up conference room, and it'll tell us things about, oh, and by the way, you should do something with the trash. And our system says trash. I never heard of the word trash before. And so it tries to ground the word trash, and it turns out that what it's sensing in the word is that there's a garbage can. Okay, just that's the way it is. So what we do is we go out and ask the person, you know, what does the word what does the word trash mean? The person comes back and tells us that that means garbage. So we're using multiple sources of knowledge. We're using GPT-3, but we're not trusting it for everything. We're going to have a human also as backstop to provide us with additional knowledge. We also then will do some planning if we can. And so then we will add to semantic memory. So the thing with GPT-3 is you have to give it a good prompt. Okay? This is the magic behind GPT-3. If you tell it the right question, it will give you the right answer. So here's if we just give it a prompt that says, I want to move the package into the cabinet. What is the next goal or subtask of move? This is what GPT-3 tells you. Very, very helpful. The next goal or subtask is to move the package into the cabinet. Apply these steps to a goal or subtask until the lowest level of the goal or subtask is reached. That is literally what it told us, okay? But if we ask it a little bit more, with a little bit more context, we say, we provide this as example. We say, move the box onto the table. What is the next goal or subtask of move? Pick up the box. Put the box onto the table. You are done. Move the package into the cabinet. What is the next goal or subtask of move? Pick up the package. Put the package in the cabinet. You are done. It's like, whoa, that's pretty crazy, okay? So this context of us sort of prompting us, giving it high activation so that its attention mechanisms are focused on the right things, it provides us with something very useful. All right, well, that's not good enough for us. We want to give prompts that not only maybe tell us what steps to do, but also give us the goal. And so we have constructed this way of prompting GPT-3. So this is part of a prompt that we give to it. Now, I mean, really, these letters and symbols are exactly what we send to GPT-3, and there's nobody out there that told us, put in a paren, examples, close paren. I think we might have seen similar things, but we decided that this worked. And it did, I mean, fine, we found out this works. So it's like you're just coming up with your own formalism for interacting with it, and it somehow says, of course, that's the way I should give my response. So we give an example. We said, we're going to give you a bunch of examples and their tasks. And the task name is deliver package. The task context is I'm in a mailroom. Aware of package addressed to Gary. Package is in the mailroom. Steps. Pick up the package addressed to Gary. Go to Gary's office. Put the package onto the desk. So this is all stuff we're just plain text going to it. And oh, by the result is of all doing this is the package is in Gary's office. End result, end task, end examples. So these are the steps, and this is sort of the goal. So what we do is then, following this, we're going to give it, continuing with the prompt, we have a general prompt we want to give, which is a task name, a task context, which is up there, and we are aware of. So we're mirroring what we already told it as part of the prompt, and we then actually instantiate that into something like task name, tidy kitchen, task context, I am in the kitchen, aware of a paper cup on the table. Steps. And now it's up to you, GPT-3, to fill in the rest. And it is extremely scary, but it does. It says, pick up the paper cup, put the paper cup in the trash can, and the result will be the paper cup is in the trash can. Okay? That's what it produces. All right, so here's the basic way we work. If we have human interaction, the human says, tidy the kitchen. The system goes back and says, what's the next goal of tidy? This is without GPT-3. We then say the goal is that the can is in the garbage and the milk is in the fridge, and then the system searches to see if it can solve that problem. It's gotten the goal. And let's say that it fails. So it says, what do I do next for tidy? Because it can't search that deep. We say, pick up the can, and that turns out to get close enough to the end goal that it goes off and solves the problem. Okay? So we're going to have this kind of interaction. What's the kind of interaction with GPT-3? All right, the interaction, we say tidy kitchen. We create that prompt that we just talked about. We send it out to GPT-3, and GPT-3 comes back with a bunch of instructions for us to follow. We then have to do a lot of interpretation of that, so we send it through our natural language system and we understand it, and then we find out that it's using terminology we don't know about, and so if we fail to ground it in this case, and we then ask the human what does trash means. The person says that object is garbage, and then it now learns the concept of trash, and then it goes off and does the rest, okay? And so now we get to see the video, and I have to explain what you're going to see in the video because it's complicated. So this is the world, this is the robot simulator, this is the interactions with GPT-3. Everything in bold is the prompt we send to GPT-3. Everything in green is the steps it sends back to us, and everything in blue is the goal that it sends back to us. So it just sends us all back. It doesn't, it just is text that comes back to us and we parse it. So this is where we're doing interaction between our agent, and then the agent is deciding to send things off and stuff like that. So hopefully that'll be clear. So this is the agent interaction window, okay? Whew. Let's hope this works. Okay, so we're going to escape out again. Okay, I'm going to stop it as we go along because it goes kind of fast. So I'm ready for a new task. The human types in, tidy the kitchen. And it's never seen that before. So we constructed a prompt based on that prompt structure I talked about, sent it off, and we got back, so this is the prompt we actually sent. We got back this from GPT-3. Take the can off the table, put the can in the trash, take the milk off the table, put the milk in the fridge. Turns out we can't put the milk in the fridge that way because we only have one arm. And it also tells us the goal. So the first thing we do is say, it gave us a bunch of instruction, but if we can interpret the goal, we can figure this out on our own, given our own embodiment, and not worry about what it thinks we can do. So we take the goal, and then we go off and try and do it. But as I said, for reasons of us being stupid, is we don't know that trash and garbage are the same thing. We could put that synonym in the system, but we just want to show that it can use the human. The human is not completely useless. All right. So then the human, as you'll notice, is the longest thing that takes the longest here. Is an object is a garbage, then it is a trash, which is not maybe the language you would have used, but it then goes off and starts searching. And this is an internal search using the actions that it has available to us, trying to solve the problem. And we set a low bound on that, sort of based on we're getting bored. And so then we go off and say, well, we didn't know what to do next. What did the GPT-3 think we should do next? Well, it said, take the can off the table. So we try to do take the can off the table. Well, we don't know what take can off something is, but we do know how to do that as a subtask. So what the human says is, well, if you want to take a can off the table, pick up the can. And so it goes off and picks up the can. Oh, yes. Whew. You never know. Well, you do know with a video, but you sort of feel like. Okay, so what's the next goal or subtask? You're done with take the can off the table. So now it's going to search again. So now that we've taken the can off the table, can we achieve that goal it gave to us? Turns out we can't. So what do we do next? Is we put the can in the trash. Well, we can interpret that because we know what trash is because it's garbage. And so we go and put the can in the trash. All right? I'm sorry, the robot does. And now the robot goes and does searching, and guess what? It's close enough to the goal to figure out how to solve the rest of the problem by itself. So now it goes off and opens the... Come on, open the fridge. It opens the fridge, and then it goes and picks up the milk. It picks up the milk. And so you'll notice it never interpreted this. It never had to take the instructions from GPT-3 about taking the milk because it was smart enough to do the search on its own and figure it out on its own. Okay? Cool. I think it's cool. Because so now you look at the number of interactions that the human has to make, and it's really shrunk. And we can shrink it further by putting in synonyms and things like that. So post-processing what we get from GPT-3. So what we see is, the possible extensions of all this is that we have an instruction, we have, our declarative task knowledge, we have our procedural execution, and this is the process we go through of interpretation, compilation. But we also could add to it, why did you do that? It has the representations in memory to explain why it did it. It did that because the pot was hot, for example. We also, down the road, we would hope that maybe one of the things we can do is offline knowledge extraction from existing curated sources, because it turns out there is a book about how to do interior guard. I think that's a long way down the road, but maybe. We can use knowledge bases, like we saw some knowledge bases this morning. There's no reason we shouldn't interface those and being able to take advantage of those. Those should help us a lot. We could learn from demonstration. I know that that's work being done here, so why not do that? We also can do verification of our knowledge base. So one of the key things that is, I said you never trust GPT-3, is maybe we can use other knowledge to try to verify it, and then also doing online adaptation. So as the system runs longer and longer, it's actually also trying to make all of its actions more efficient. And then it can possibly be monitoring its behavior to make sure it doesn't do evil things. So that's another thing that I think is important down the road, is that we want to have always the ability to specify what we call abstract behavioral constraints. So not just do this thing, but here are things you don't want to do. And it's more than avoid running into people. It has to be at an abstract level where you have to think about how you instantiate it in this current situation. And we have an active research problem there. Anyway, so let me end with questions and discussion. And
thanks for awesome talk. It helps me to put things into perspective. One of the questions I have is, in ITL scenario, you have the problem of common grounding, right? So the teacher and the student has to have common level of understanding. Like one of the example of your human instructions that you wrote, the trash is something that if the object is garbage, right? So do you have some sort of list of concepts that are already being learned on agent's point of view, right? So the human teacher knows.
Right, so I think that's a challenge. So one of our projects is actually flipping this around, upside down, is to say, what can the agent do to help the teacher give it good instructions quickly? So how can you be a good student? And so we're actively doing that, and you don't want to be too heavy-handed because then you're having this robot just talk to you all the time. Here's something I just learned yesterday. Well, I don't care. So, you could go talk to your other robots about that. But how? And we're going to do some experiments where we try to figure out when is a good time for the robot to tell the human things, and what kinds of things would be useful for the human to hear so that it can give instructions better. And I'll do all this without disrupting the experience of the interaction. So yeah, I think that's an important problem and one of the things we're looking at.
Okay.
Michael's next. Oh, you're in charge.
You want to catch?
Thanks a lot for the talk. I wanted to ask about what your impression of GPT-3 is in terms of action sequences, right? So it seems like the action sequences that are something in recipe-like or step-by-step instructions are fine. Probably it couldn't do things like that require more planning, right? And it would probably not be able to kind of be very smart in terms of how to execute things.
I wish I knew,
Yeah.
but one of the hard things about these systems is to know whether, oh, we did tidy conference room, everything's there, and it's a common task, or maybe, and so it has a lot of knowledge in it. So this is a different, slightly different issue, but you go into a different domain, you don't know ahead of time whether it's going to know anything useful at all. Theoretically, if it's a common domain that people have talked about in books and on Reddit, then yes, there will be good things to mine there. I also agree that it's likely that for anything, so it's going to be this sort of amalgamation of things it's gotten from many different sources, and so it's not exactly the least common denominator, but the instructions you get are going to be sort of generic. And so as we talked about, that the instructions were not specific to our robot, which has one hand, because it has to go and open the refrigerator door before it can grab things and put it into the refrigerator door. So that's why we think it's really important. That's why we want to get the goal if we can. And we also saw the goal was incomplete, because the goal didn't tell us to close the refrigerator door. And so so that's why we sort of say, yeah, let's use it as much as we can, but we want the human always there. And we also want the planning there, because without the planning, it gets really tedious for the human to have to step it through. So the planning makes it so you're not teaching a stupid thing. You know, you tell it to do something, it figures it out, it's like, oh, that was nice. Whereas if I have to walk it through every step, it's a problem. So I do not know. So one of the challenges of working with any of these language models is you do not have a good sense of the density or quality of the procedural knowledge that you're trying to mine until you go out and ask for it. I assume that's the same as your experience.
Yeah.
But on the other hand, it's got some gems. So it seems like you want to be able to take advantage of it if you can. Oh.
Hi, thank you for the talk. One question that came to mind when I saw the Towers of Hanoi was, so SOAR kind of has a search space for the actions with the effect, I assume, and after a certain height, the search space gets too large, as you said, right?
Right, so in that case, we're monitoring, we're only searching to a given depth, and if we exceed the depth, then we ask the human for help.
So my question would be, have you looked into generalization of such problems? For example, the Towers of Hanoi are always solvable, right? And the algorithm is very clear, just...
Right, but no, it's not. There's multiple algorithms for towers in Hanoi.
Yes, of course.
And that there's ones that are much better than others depending on how much you want to think. So, yeah,
yeah, well, there's a general way to always solve Towers of Hanoi, right? You can do it with a height of 1 million pieces.
Right. So it's a search-based task. So if I search deep enough, I'll find.
But you haven't looked into find a general algorithm, right? You're just looking in the search space.
That is a general algorithm.
Okay.
Fine. I'm being difficult. No. We have not looked at then, once we are working on a task, can I discover heuristics or some structure to the task that we can exploit so that the search is more efficient? And that's the question you were asking, and I was being a jerk. So I'm sorry. So that is definitely something that you would want one of these systems to be able to do, but that's a whole nother research program, which is how do you, once you've gotten a new task, how do you analyze that task to try to discover the regularities in it and what are effective heuristics for doing search in it. Even, say you wanted to use A* for some task, Tower Noi, you don't want to use A* necessarily, but how do you decide what a good estimate to the goal is? Well, that's, a hard problem, and people have done research on it. And it would be great to build a system that not only is learning new tasks from scratch like we are doing, which is sort of the bare bones, but then would be able to do these extra things, which is learn the task structures and things like that. So, yeah.
Okay, thank you.
Note to self, don't be a jerk in answering questions. Okay.
Hi, thanks. Okay. You were talking about experience, and you have experience in that architecture, and you're augmenting that with GPT-3. We heard that it's not very important that the robots, or it's not usually that the stuff that the robot learned is kept and talked about, and yeah, well, I learned that new thing, well, go talk to your other robots about that, that's fine. But I can't also imagine that GPT-3 is very deterministic, so it's context dependent, and it gives different answers depending
it's
on
non-deterministic, is that
yeah,
what you're saying?
yeah, that's what I can imagine, because, well, you can query it, and it gives you an answer. Probably it's a very good answer, and depending on how general it is pretty general. It gives a recipe for how to achieve things, so this is diminishing the non-determinism. Maybe it's pretty deterministic, but in the end, what my question is, it's twofold. One thing is, how deterministic is the recipe that you really get from that context dependently, and have you encountered situations where you get different answers depending on the context? And the other thing is...
One question at a time.
Okay.
Let's handle that
Let's
question.
do that. And
Okay,
yeah,
so number one, GPT-3 has a temperature, so you can set the temperature, which is like randomness. And so we usually go with a temperature of 0, meaning it's pretty, it is deterministic, but one could imagine, and one of the things we want to look at is not just get one answer from GPT-3, but let's get a bunch of answers from GPT-3, and let's compare them to see how consistent they are with our existing knowledge. And then, for example, another strategy we're using is we ask for only the next token from GPT-3 at a time, as opposed to all of the instructions, and then we check to see if we get that token, is that a concept we know about? Is that an action we know about? If it's not, then we say, give us another token in place. And so we do another query and try to get another one, so that we see if we can get GPT-3 to tell us things in our language. And so that actually improves things a little bit. And so you do get non-determinism from it, and it is sensitive to the exact form of that prompt and to what we put in the prompt. And one of the things we do research on is, can we then do, can the system learn how to give better prompts given the situation it's in? And so there's all these new problems you never had before. Usually when you interact with a database, it's like, yeah, this is the kind of query I want to make to get stuff out of that that database. With GPT-3, it's a wild west. Okay, question number 2, hopefully.
Yeah, directly building on top of that. If you know the query and you know the context, this is a pretty complex setup in certain situations, but you know that query because you may have asked it before. And this may be some kind of an
Then we don't need
experience.
to ask it again. If we've
So,
asked it
yeah.
before, we will have learned everything we can get out of that
But
query.
only at runtime, or do you store it into your episodic memory and your experience such that you don't even need to ask that query in certain situations?
Well, if it's a
at all
different
anymore?
situation,
Well, if it's a different situation,
then
it's a
we'll
different
have to
query.
ask the question again. But if
Yeah.
it's in the same situation, we will know how to do the task, and we will not have to go out to GPT-3 to ask it, okay?
Cool.
All right, and so let's end, so I'm out of time, except, what do you really care, what do you really want GPT-3 to do for you? Well, I'll tell you what I want it to do. I want it to tell jokes about SOAR. So, if you make the query to GPT-3, the SOAR cognitive architecture and a rabbi walk into a bar, and everything else is generated by GPT-3. After a few drinks, the cognitive scientist and the rabbi begin to discuss how to program a computer to understand and reason about the world. I've heard that you people have been working on a cognitive architecture called SOAR, says the rabbi. That's a pretty impressive name. I've always been a fan of acronyms. Yes, says the cognitive scientist, it's a pretty impressive acronym. Do you think it's possible to build a computer that can understand the world the way a human can? Asked the rabbi. I think so, says the cognitive scientist. So, says the rabbi, can it understand the Talmud? And I mean, that is so on point. I mean, it waves around a little bit, but that could be a real joke. Or sort of, I don't know what it is, but it's a real thing. Now, this was not the first thing it said. It was not the last thing it said. This was one of maybe 20 that I picked out. But this is a second one. The cognitive architecture walks into a bar. This is a joke that has been told in computer science circles since at least the 1990s. I mean, you all heard it before. The SOAR cognitive architecture is an example of a connectionist model of cognition developed by John Doyle and Peter Dion at the University of College of London, completely made up, and was one of the first published models to be designed specifically for the study of human cognitive architecture. The joke, so this is meta. The joke relies on the fact that the traditional cognitive architectures such as SOAR described in the literature are described as intelligent, and as such, they must be able to walk into a bar and order a drink. The joke relies on the fact that connectionist models of cognition were not conceived of intelligent. As such, the poor cognitive architecture would not be able to walk into a bar and order a drink. The joke was popularized after it was described by Robert Trappel in his textbook on cognitive architectures, and has since been included in numerous other textbooks on cognitive architecture. And to date, it has been described in the literature as the classic joke. I am done. Next time I come, I'm hoping that GPT-3 does not write my talk, but who knows?